so it starts to flow through, and the end result is that you sort of squeeze the container that was holding all that blood at the very end. But that's just sort of for good measure. Make sure you get the last 25 to 30% out of the atrium. But most of the blood that enters is basically just going down a pressure gradient. There's a lot higher pressure in the atrium at that time compared to the ventricle, so it's going from high pressure to low pressure. Yeah, the P wave is depolarization of the atrium. So the atrium and the ventricles are going to be depolarized, which means they're going to be getting an electrical signal that tells them it's time to contract, and they do it in order. The atria are going to depolarize before the ventricles. So that's why the P wave is basically telling the atrial muscle to contract, and then the QRS waves are going to tell the ventricles. But we will have a whole lecture on electrocardiogram and the QRS too. Yeah.
Why can't you use a defibrillator for atrial fibrillation?
So that's a good question. It's not so much that you can't. It's that atrial fibrillation a lot of times will resolve on its own. Sometimes it's caused by an ectopic pacemaker, which is just another part of the atrium that happens to be a little hyperactive and is contracting before, or sending a signal to contract before you have the sinal atrial node sending that signal. So you start to get rapid fluttering. And because biologically it's not as detrimental as ventricular fibrillation, you're kind of weighing out the benefits of shocking the entire heart in order to get it started. Now, that doesn't mean that it isn't necessary. My brother had AFib, and he had to have his heart shocked a couple of times in order to get it back into sinus rhythm. But sometimes it will go away on its own.
So the resistance of the systemic circulation is controlling that decrease in the pressure from the isovolumetric relaxation to the time you go back to the contraction. Does that change? Because if your heart's beating like twice the normal rate, it seems like you won't get as much pressure reduction. I mean, if that curve is fixed, it doesn't seem like your ejection fraction will be as good if your heart is beating really fast as if it's beating really slow.
It won't. It won't be. If you elevate your heart rate, you will reduce your ejection fraction because you're decreasing the stroke volume because you don't have as much time to be able to fill the ventricle to capacity before you squeeze it out.
So, follow-up question: if I'm actually measuring with this moment, or whatever, my blood pressure, and my heart is beating like 100 beats, I'm going to get a higher diastolic pressure.
Probably. All right. Any other questions? Okay. Okay. All right. So, quick question. We touched upon this a little bit, but I want you to, this is a matching question. Take a look at your A, C, and V waves, which I didn't talk about yet, specifically because I wanted to ask you first. Match what you can about what is happening in the atrium. What do they correspond to? You guys still have this open? Sorry about that. Couple more seconds. All right. All right, so show our results. Okay, so we actually had about 19% that ended up with the correct. That A valve, or that A wave, corresponds to what in the atrium? It's right toward the end of diastasis. And I don't know if I can draw on this, but I can point it out right here. Atrial systole. Okay, so right there, we have the A wave is due to contraction of the atrium. The C wave, we actually touched upon a little bit ago. What happens when you start contracting the ventricle? You get bulging of those AV valves. When the ventricle contracts, it basically puts pressure on the valve. They don't prolapse into the atrium because they're held in by what? Carotid tendon, which are connected to what? Capillary muscles. Capillary muscles contract in order to hold those heartstrings and make sure that those bulging valves don't prolapse into the atrium. So that's what's responsible for your, I guess for that C wave. The V wave is that slow and steady increase in overall pressure. That is what's happening as we are moving through our, sorry about that. As we're moving through the blood coming from the venous circulation into the atrium, that slow increases as the atrium is filled. Okay, so your A, C, and V are basically the ways that are happening in the atrium relative to this massive diagram on what's going on in the ventricle. All right, so we touched upon this already. Systole, you have the ventricular muscle is stimulated by an action potential, and it is contracted. Diastole, you have relaxation of your ventricular muscle, and you have the gradients are being repolarized, your sodium gradient, your potassium gradient, and calcium gradient, all of which we're going to get into in future lectures. Just an introduction to that. The muscle cells themselves are starting to relax. For the ECG, the P wave that we're going to observe is going to be your atrial depolarization. QRS is your ventricular depolarization, and your T is the repolarization of the ventricle. So systole, as I said before, just to highlight the specifications that you're starting at the beginning of contraction. Yeah. Good question. No, it was just starting at the beginning of contraction, so it includes isovolumetric contraction as well as the full ejection phase before you start isovolumetric relaxation.
The B wave, is it the entire upward slope?
Yeah.
Or is it only just
It's the upward slope. It's the entire upward slope. Diastole, same thing. You're starting with the beginning of that relaxation, which is happening in that isovolumetric condition, all the way through the completion of diastasis. This is what I was telling you about, that we would have a figure that showed the difference between the right and the left. So, once again, pretend that you are looking at a person when we're looking at orientation here. This is your right heart. Sorry about that. And this is your left heart. Part B is what we just looked at. The Wigger's diagram we looked at showed 2 cardiac cycles. This is showing 1. This is basically everything we just talked about. It's color-coded, so I kind of liked this one as a way of being able to see exactly what is happening at each stage inside of the heart. But you'll notice that the right heart, okay, the right heart has a major difference. The biggest part that's the same as you're looking at the bottom, the ventricular volume, it's the same. Both sides of the heart are pumping the same amount of blood. What's the biggest difference between them? Absolute pressure. Okay? The biggest difference is the absolute pressure between the right and left. You don't generate as high a pressure on the right side of the heart. Why? It's only going to the lung. It's not going very far. It doesn't have a reservoir of blood hanging out on the other side of the pulmonary valve the way that the aortic valve does. So you don't need to generate as much pressure to overcome that afterload, and you don't need as much pressure in order to get through the circulatory system in the pulmonary system. The other big difference is these parameters here. Let me see if I can circle that here. That's the other big difference. And this is sort of what I was talking about before, introducing a little bit about the heart sound. Even though there is a little bit of a difference between the right and the left in terms of the timing of the closure of the atrioventricular valve. You can hear a little bit of that change. It's not usually as audible, but you can hear the difference between the closure of the right side versus the closure of the left side. Typically what's going to happen is your left side is going to close just a little bit before the right. So you can hear, if you listen very carefully, you can hear the closure of each valve because there is a slight difference in the timing. That physiological splitting that I mentioned for the second heart sound, which is the green, column, that is something that can be heard often, mainly if somebody tells you to take a deep breath, right? Inspire in, you can hear that physiological splitting. You can actually exaggerate the ability to discern from our own ear the difference between the closure of the aortic valve followed by the closure of the pulmonary valve. So there is a slight timing difference between the right and the left side, but the width of each of these, this is isovolumetric contraction, isovolumetric relaxation. Why do you think the red column on the left heart is so much wider than the red column on the right heart? What's happening?
It's a lot more pressure to go through to get up to that.
Exactly. That's your isovolumetric contraction period, right? So it's just going to take more time to generate that amount of pressure from the contracting muscle cells. Doesn't take as much time to get up to the pressure that you need for the right side. So same thing, not as big of a difference in the isovolumetric relaxation side of things, but there is a decent difference in the isovolumetric contraction between the right and the left because of the amount of time it takes to generate the full force of the pressure to open that other valve. Okay, so I think this one was from the Boron book. The other Wigger's diagram was from the Geithner-Cole book. Yeah, sorry.
On those little annotations where it's saying how the AV and similar valves are closing and opening, those are just arbitrarily placed. It's not referencing the pressure.
Oh no, it's representing the vertical line. It's pointing to that vertical line, saying that the pressure within that line. No, right at that line. Because you see, if you look here, you're talking about like this closing and this opening.
It's like those are above the pressures that are
Right. It's just because they don't want to get in the way. Basically, this pulmonary valve opening here is pointing to this dashed line, and this is pointing to this dashed line. So you basically would just follow it down to see what the pressure was. Yeah. So it's the same information that we saw on the Wigger's diagram. It's just written a little bit differently. It's pointing to that, whatever's happening with that. There it is. You can't see it because the depolarization of the ventricle is basically loud and blustery, and it overshadows any repolarization wave that you might potentially see from the atrium. So it doesn't actually show up on your ECG. It's happening, but it's happening at the same time as depolarization of the ventricle, and that's a big loud mess. Yeah.
Actually hearing the depolarization or the actual
Contraction. Well, what you're actually hearing is the closure of the valve. You're not even really hearing the contraction. That said, you can sort of hear the contraction in the other heart sounds, but you can also hear filling, and it has to do with what you're actually listening to is how the heart as an organ or as a muscle is actually functioning. You're not really hearing contraction, you're hearing the effects of contraction. Okay, or you're hearing the effects of stretching, which I'll get to in just a second when we get to the third and the fourth heart. Any other questions about this? We're doing pretty good on time, so. All right. This is actually from the Barn and Levy book. Any figure that you see that has this blue, I guess, faded background, that's Barn and Levy. This one is just sort of a close-up to show you a little bit about the ECG and the phonocardiogram, the stuff we talked about with the heart sounds, the first, second, and third, and fourth heart sounds. The figure that the table I wanted to point out is this one. This will really outline exactly what is happening at each point. We already talked about the first sound. The first sound, you get a burst that comes from your mitral and a burst that comes from your tricuspid. So you'd be your M1 and your T1. That is telling you the timing of the closure of those two valves. And that is your first sound. It is also the loudest sound. The second heart sound, that's your dub. That is the closure of your semilunar valves. And again, you can have physiological splitting. It's a little hard to hear, but if you get somebody to inspire rapidly, then you can actually hear it a little bit better. But both the first and the second, because it's generated by the sound of two separate valves closing, and they don't close exactly in synchrony, you can hear or detect that slight difference between the timing of one versus the other. And it's always going to be the left side closing before the right. All right, the opening snap. Anybody know what stenosis is? So stenosis literally is the hardening. So if you have a stenotic vessel, it's hardening and it will actually make it a smaller opening. Stenosis of the mitral valve is usually from crystal deposits and stuff that will end up on the valve itself, so it's less fluid movement and it becomes more rigid. So when it becomes more rigid, you can actually hear it open. That would be something that you can actually hear listening to that opening snap. You can hear that sometimes if somebody has mitral valve stenosis. The third heart sound, this is called the ventricular or protodiastolic gallop. It's only really called that because you're looking at the closure. The S1, S2, S3, it goes 1, 2, 3. So it's like a gallop of 3 sounds in a row. Okay, but you're starting with that loudest sound of all, and then you hear that third sound coming afterwards. That's why it's your ventricular gallop. And it's the sound of filling of the ventricle when there is some kind of limited distensibility. So it doesn't necessarily mean that it's pathological, but it's not something that you hear all that often. You tend to hear it more in infants than you do in adults, but it is really just the diastolic filling of the ventricle. And as the ventricle continues to fill, sometimes you can hear that because of as the blood's coming in, you can hear it sort of reverberating or recoiling off the ventricular walls that are starting to lose their distensibility as they're getting to their maximum filling. Distensibility. So if something is distensible, it's stretchable. It's able to be stretched, elastic. Yeah.
Would that sound become more prominent in like people who are tachycardic because the heart is constantly reverberating as you breathe faster, would you hear that sound louder? Or
So that sound has more to do with the filling. And you'd actually, if you are tachycardic, you're not really filling to capacity, so you don't really have a problem with distensibility in terms of stretching all the way. If you have a problem with hardening of the walls, and it's not, for whatever reason, scar tissue, infarction, anything that causes it to not have the same properties, what you're hearing is the blood trying to come in and sort of pushing off against a wall it doesn't want to stretch. Yeah. All right, fourth hard sound, that's basically your atrial or presystolic gallop, and it's because it would come before the lub dub. So you hear the S4, then the S1, and the S2. It's still that 3 sounds in a row. It's just that now S1, the loudest, is not the first one, it's now the second one. This is typically something that is a pathological condition. If you have an unusually strong atrial contraction in response to severe limited distensibility of the ventricle, then sometimes you can actually hear the atrial contraction. That's actually what you're listening to, the force of that contraction, forcing any blood into a ventricle that's not able really to accommodate. But that's typically a pathological condition. That's not something that you should be able to hear ever. But it is something that does have a name, so it occurs often enough when people start to end up with heart disease. I forgot to define one thing. Do you guys know the difference between ischemia and infarction? I realized it's... Okay, so what's the difference? Ischemia is lack of oxygen because of its lack of blood flow. So ischemia is really lack of blood flow to a particular tissue part to particular cells within a tissue. What's an infarction? Death of those cells because of a lack of oxygen. So ischemia prevents oxygen and nutrients from getting to it because it's basically stopping blood flow. So it's taking away the life source, right, for those particular cells. The infarction is death of those cells in response to that lack of blood, that lack of oxygen. So when I start using ischemia and infarction, I want to make sure that that was clear before I started kind of rambling on. All right, so how are we on heart sound? Better? All right, next question. For those of you that did not do 503, this is really just going to test any information that you have in your academic career on sympathetic and parasympathetic. For those of you that did 503, the blue curve is your normal level of sympathetic stimulation, baseline sympathetic stimulation. What would A, B, and C be? Oh, yeah. All right, looks like it cut you off. So here we go. Gotta scroll down. All right, good. 46% got it completely correct. Hmm? A, B, and C from top to bottom. This is it, actually labeled.
Which was the letter choice and which was the answer?
Oh, so it's ABC. Yeah. This is question 1, option B on your thing. I get so it automatically changes up when it rearranges the order anytime, every single time that I run the class. It'll change the order of any multiple choice questions. It just happened that the answer choices were A, B, C, and there were multiple choice questions for A, B, C. So yes, it's A, B, and C. Maximum sympathetic is A. The zero sympathetic is B, and then the parasympathetic is C, which is what we're looking at here. Yep. Okay, so yes, if your normal stimulation is that purpley part there, which is a different color than the previous one, I apologize for that. I obviously switched the colors around when I read you it. That is just baseline what you always have in your body. You always have some level of sympathetic stimulation. So there are multiple ways that you can control whether or not you ramp up that fight or flight response or when you get to that rest and digest response, which is your parasympathetic. So cardiac output, this is looking at right atrial pressure. If you're looking at cardiac output and you maximally stimulate your sympathetic system, it's going to ramp up your cardiac output. The normal cardiac output is somewhere around 5 liters per minute. You can get up to 15, 20 liters per minute, depending on what the situation is. You ramp up sympathetic stimulation, you really increase the amount of cardiac output that you can have. You can remove the normal baseline sympathetic stimulation and get no sympathetic stimulation, and that can help to reduce the overall cardiac output, or you can specifically stimulate the parasympathetic system, which actively slows down the heart rate and reduces the contractility. Your vagal efferents are typically going to innervate the atria, so it's going to have an impact on overall heart rate. It doesn't have as big of a change on the contractility, but it does have the ability to slow down your heart rate. All right, now we're going to get into the PV loop. On the left, what does that look like? Figure diagram. That's basically all it is. The right side is when you take the left side and you plot them against each other. So you're taking your volume and your pressure, and you are going to plot these two against each other, where you end up with pressure and volume. If you take every single point on the graph on the left and you plot those two values against each other on the right, you end up with your pressure volume loop. That PV loop is going to tell you a lot of information about what is happening inside of the heart as your cardiac cycle is occurring. One turn of the loop is a single cardiac cycle. It's relating volume against pressure. Instead of having them as two separate things with time as your x-axis, it's now saying what happens to the heart when you are at this particular pressure. What's the volume? What is the pressure that you get when you have this particular volume? Okay? There are two lines that are on the right-hand side that I want to point out. They are lovely dashed little lines that are going to become important. We have our ESPVR and our EDPVR. EDPVR, end diastolic pressure volume relationship. Basically, for anybody who had any kind of muscle physiology, this is your passive tension curve. We're looking at those tension, length tension relationships. EDPVR is basically your passive curve. ESPVR is your end systolic pressure volume relationship. That is equivalent to your total tension. The biggest part to look at here is your EDPVR shows you the relationship between pressure and volume during diastole at all of these different volumes. That is the max pressure that is going to be generated at each one of them. It'll show you the limit to which the muscle can stretch. If we're talking about end diastolic, is the ventricle full or empty? End diastolic. So it's relaxed. What happens when your ventricle relaxes? Infill, right? Or contraction. So end diastolic volume, or the end diastolic pressure volume relationship, is showing you at what volume that ventricle can hold That's why it curves up a little bit at the end. That's the max. You can't shove any more blood in there if you try. It just won't stretch any further. The end systolic pressure volume relationship, by definition, is the maximum amount of pressure that this heart can generate at a given volume. So your PV loop can never cross over that ESPVR. Because by definition, that's the maximum pressure. You can't have a pressure that's above that at a particular volume. Okay, so your PV loop will always go up to it, but it will never cross over. All right, another question. This one is a fun matching one. All of these lovely things are happening. You guys can talk to each other. I want you to see what you can think of and what you can remember or deduce is happening based on what you know about the cardiac cycle. What's happening in terms of how the pressure and the volume are related to each other at each of these points. How that? Give you about 2 minutes.
Did you open that window? I just clicked it and then zoomed in. Oh, just do that. I zoom in and get small. No, I lost my. I lost my answer. This is tough, dude. Look, I'm on the question. I don't have any answers. Yeah, I lost mine too. This sucks. God damn it. Oh my god, it just gets worse. Look, she doesn't have one more either. I hate doing that. I'm paying her to use this. It's broken ass. I feel like I know it. I just put the answer choices back up. Okay. Well, I'm not gonna say anything. I'm just gonna watch that. My left eye's been twitching for like days.
All right. I see nobody has responded. But that's okay. We will just.
Because you took away the answer choices.
It's not opening. It's supposed to allow you to answer.
I'm just
The answer
gonna
choice.
submitting. Yo, this is not
On yours?
stupid.
Oh.
That's fine.
Ah, okay. Well, that explains why nobody was answering me. Okay. Well, then we'll just move along. All right, so first things first. How many people remember how you calculate work? Area under pressure volume curve. The area under the curve is basically how hard your heart is working. It's also force per unit squared, but in this case, you're looking at the pressure change over the change in volume. That is your PV loop. So let's talk about what is actually happening at each one of these points. So let's start with point A. What is happening at point A? We are at a low pressure, bottom of that line, and we are getting ready to increase volume. We're at the lowest possible volume, right? We're down to about 75 mils on that ventricle. So what is happening here? Yes. Close it. Okay. What's happening between A and B? It's still closed, but what's happening to your ventricle? It's filling, right? The pressure is going down, but the volume is getting bigger, right? You're moving along the x-axis. So what is happening between A and B versus B and C? A and B is what stage? If you just close the mitral valve, what's happening now? Rapid filling. Okay? So you close that mitral valve. Oh, sorry. You've closed. Sorry, open. Open. Sorry, I was thinking over here. You've opened that. That's my bad. I was looking at the C, and as I was writing, and I wrote C, and I was like, mitral valve closed. The mitral valve is open here, and you are allowing that blood to come in. Okay, sorry, that was my fault. I usually start at the mitral valve closing because that's where we started the Wiggers diagram, but I started at a different spot, so that's my fault. I apologize. Forget that part. Point A, mitral valve is open. Okay, you are now at that lowest point of your pressure. If you're at that lowest pressure point, you drop below the pressure inside the atrium, so you've allowed that to open up, and now you get blood coming in. Volume is going to increase. So this is your rapid filling phase. Oh, I don't know why it's making rapid filling versus reduced filling. Now it's point C, what's happening? Your mitral valve is closing. Yes. It's going to close. Sorry. That's not helpful. All right, so your mitral valve is closing at point C. What is happening in that little blip before? That little tiny curve. That's your atrial contraction. Why? You're getting a slight increase in volume, and what's happening? Why do you get that curve? What's also increasing? Pressure, right? So at that little hill right before C, that's your atrial contraction. Now you have completely filled, you're at 150 mils inside of the ventricle. You've completely filled up that chamber. Now what's happening? You close that valve, so both valves are closed, and what is going on? You're not changing volume, but you are changing pressure, and you're doing what to it? Increase or decrease? Increasing it, which means what? Isovolumetric contraction. That is your C to D. C to D is isovolumetric contraction. And then what happens at D? Your aortic valve opens. And because your aortic valve opens, you end up with a decrease in volume. You get an increase in that pressure as you are contracting and forcing out that blood. Why are you getting that increase? It's the same thing as if you try to exhale just by blowing out air versus exhaling through a straw. It's harder to do it. Smaller tube. You're exhaling through the valve, the aortic valve. So you have this rapid ejection that's happening from D to E. So very fast loss of your ventricular volume because it's being sent out. You get the reduced ejection that's happening from E to F because you started to relax those muscles. Your T wave has already started to repolarize the ventricular muscle. You get that reduced ejection. What happens at F? Aortic valve closes because now you're at your minimum volume. You've lost that pressure below what the aortic pressure was. And now you have from F to A, that's your isovolumetric relaxation. So drop in pressure with no change in volume. So same exact cycle that we talked about with the Wiggers diagram, but looking at it as change in pressure specifically as it correlates to what's happening as to the volume at that particular time. All right, we will finish up the last bit of